Welcome to my presentation of Materiality of Mobility, which is a case study for the City of Vienna in Austria. This case study uses a stock-driven or bottom-up approach for quantifying mobility stocks and combines it with a stock flow service nexus approach. We quantify the mass of mobility stocks in Vienna, material flows for expansion and maintenance, primary energy use of mobility, greenhouse gas emissions induced by mobility, and the mobility services for 4 different modes, which is pedestrian mobility, bicycle mobility, public transport, and motorized individual traffic. And we present insights from a stock flow service nexus approach and planned policy measures targeting mobility in Vienna, which also confirm the high resource intensity of motorized individual traffic, not only regarding energy use and emission intensity, but also regarding material stock and flow intensity. More than 2/3 of global energy use and 3/4 of energy-related CO2 emissions stem from urban areas, and the resource use of cities is expected to grow even further. Although megacities with more than 10 million inhabitants receive most attention in sustainability science, medium-sized cities are actually more important as they incorporate larger shares of the world population and as their size allows also more flexibility of urban development. Vienna is an example of a medium-sized city with 1.9 million inhabitants. Mobility stocks persist for long times and therefore create path dependencies, because if mobility infrastructure is built in a certain way, this leads to more people choosing certain mobility modes. Stocks furthermore store capital and resources and can therefore be used as a secondary source for materials for urban mining. In Vienna, transport emissions have been growing faster than total greenhouse gas emissions, and since 1990 this was an increase of 59%. Also, traffic produces other emissions relevant to human health and the environment, such as particulate matter, nitrogen oxide, or carbon monoxide. Also, the city of Vienna is growing and the greater region around it as well, where the potential commuters live. So acknowledging its responsibility to contribute also to the UN SDGs, the City of Vienna aims for a CO2 neutral transport sector until 2050 and for a reduction of the related per capita final energy consumption by 70%. This analysis uses a material and energy flow analysis, building up on the concept of social metabolism, and follows a mass-balanced approach. So inputs have to equal stock additions and outputs. We analyze mobility stocks using a stock-driven or bottom-up approach, that is starting from an inventory, for example, of roads and applying material intensity factors. Thereby we cover mobility stocks of infrastructures such as road, railway, subway, tram network, and also interfaces of vehicles such as cars, bicycles, trains, trams, or buses. We quantify material flows for maintenance, expansion, as well as primary energy use and emissions linked to personal mobility. And we compare a number of stock flow service indicators for the 4 different mobility modes: pedestrian, bicycle, public transport, and motorized individual traffic. This is the methodological framework to investigate the stock flow service nexus of personal mobility in Vienna. It's based on the conceptualizations by Havel and Carmona and colleagues. The system boundary, which you see as a gray dashed line, is the administrative city border. Mobility transgressing this administrative border of Vienna is included to the extent that it takes place on Vienna's territory. So also cars entering or exiting the city are included to the extent that they move within city territory. Within this nexus conceptualization, personal mobility functions and services, which you see at the top, are provided through combining mobility stocks of infrastructure and vehicles and energy use, for example, of fuels or electricity that power mobility, while generating greenhouse gas emissions. This is represented in the blue lines 1 and 2. And also, annual flows of materials for stock expansion and maintenance are necessary to ensure the functioning of mobility stocks, which you see labeled in orange as connection 3. In an average year between 2010 and 2018, the material stock of Vienna's mobility system had a total mass of 99 megatons. As you can see here in the graph, the largest stock item was traffic surfaces with 52 megatons, including roads, pedestrian zones, sidewalks and cycleways. The second largest stock item was the parking infrastructure, but excluding parking spaces on roads which were already included in the stock of roads. This was 21 megatons, followed by the subway system of 14 megatons. In terms of material composition, 95 megatons or 96% of mobility stocks consisted of non-metallic minerals such as aggregates, gravel and sand, asphalt, concrete, bricks and glass. Metals accounted to 3.4 megatons, of which the largest part was iron and steel with 3.1 megatons, followed by much smaller amounts of aluminium, copper and other metals and alloys. The majority of mobility stocks were infrastructures with 98 megatons, which consisted mostly of aggregate, concrete and asphalt and smaller fractions of steel and other metals. Interfaces or vehicles only accounted for 1.2 megatons of mobility stocks, so about 1%, and had a more complex material composition, with steel accounting for more than half of the stock of interfaces, other metals and alloys for 15% and plastics for further 12%. Concerning the usage, 70% of mobility stocks in Vienna were used by motorized individual traffic. Public transport used 18% of mobility stocks, of which the subway system was by far the largest part. Cycle paths and other traffic surfaces used by cyclists, such as parts of roads or pedestrian zones, accounted for 2% of total stocks, and further 10% were allocated to pedestrian use due to the large mass of sidewalks mostly. Combining the results of material stocks with results on material and energy flows, emissions and mobility functions and services allows comparing stock flow service indicators. This provides insights into the characteristic of different mobility modes. Unsurprisingly, motorized individual traffic shows the highest primary energy intensity per trip, which you see in graph A at the top left-hand side, and per person kilometer or functional unit, which you see below in figure B. The energy intensity of public transport is 62% lower than the energy intensity of motorized individual traffic on a service level and 57% lower on a function level. The same holds true when looking at greenhouse gas emissions in figure C and D. Emissions of public transport are 77% lower and 74% lower respectively. The indicators stock intensity of services and stock intensity of functions displayed in figure E and F provide insight into the stock use of different transport modes. Motorized individual traffic shows high values for both indicators, meaning that large material stocks are required for providing one unit of service or function. Stocks for pedestrian mobility show worse performance in terms of stock intensity per person kilometer, but are superior to all other mobility modes on a service level. This is because of the large number of pedestrian trips compared to their low total distance in kilometers. Public transport is highly efficient in terms of stock intensity of functions as well as services, because these stocks are used for large numbers of trips, and in contrast to pedestrian mobility, also for longer distances. Looking at figure G and H, we see that public transport is also highly efficient in terms of material flows. Compared to motorized individual traffic, public transport requires only 9% of material flows per trip and 15% per person kilometer. Again, maintenance intensity of pedestrian mobility strongly depends on whether a service or function perspective is taken. Pedestrian maintenance intensity is highest among all mobility modes per person kilometer, but quite low compared to the number of trips due to the low average distance of pedestrian trips. This visualization summarizes the stock flow service relations for the 4 mobility modes investigated. We plotted the share of each mobility mode in % of total mobility stock, which you can see on the top chart, of total trips as a proxy for mobility services and of person kilometers traveled representing mobility functions, which you see on the left-hand side, and in percent of total energy flows, emissions and material flows, which are displayed on the right-hand side. We find that both active forms of mobility, represented in green and blue, as well as public transport, which is represented in red, shares of mobility services are proportionally higher than shares of mobility stocks, flows and emissions. Public transport provided the highest share of total mobility services with 38% and an even higher share of 45% of total mobility functions, while using smaller shares of mobility stocks, material flows and energy flows, and generating a lower share of total greenhouse gas emissions of mobility. Motorized individual traffic, the grey part, was the only mobility mode requiring more stocks, material and energy flows and generating more emissions than delivering services. With this analysis, we presented a novel perspective on resource requirements of mobility, which emphasizes the high resource intensity of motorized individual traffic, not only in terms of fuel demand and greenhouse gas emissions, but also regarding material stock and material flow intensity. We used the number of trips as a proxy for mobility services, which is a first step in overcoming the focus on distances traveled, because longer distances are not necessarily a contribution to well-being and therefore not understood as a service. We have seen that this perspective changes stock flow service indicators, especially concerning the active modes of pedestrian and bicycle mobility. Pedestrian mobility, for example, enables people to reach a considerable share of destinations, almost a quarter of total trips, while only 4% of total distances are traveled. We are aware, however, that using the number of trips as a proxy for mobility services is also not a perfect solution, because not all trips are equivalently important, first of all, and not all of them could be performed with any mobility mode. So we suggest considering both function and service-based indicators. And there are, of course, many promising extensions for such an analysis. An exergy analysis of stock materials, for example, the inclusion of upstream material demands for building up material stocks and providing material flows for maintenance, the assessment of associated benefits such as displeasure or pleasure of traveling, time savings, health effects or environmental impacts, and including a spatially explicit analysis seems an interesting further development. As mentioned before, the City of Vienna has formulated ambitious sustainability targets for the traffic sector. In doing so, our result suggests that first, prioritizing infrastructure-focused measures is important. Especially targeting traffic surfaces seems promising, as they comprised 53% of total stocks and required 64% of all material flows for maintenance, and are therefore key to improving material efficiency of mobility. Measures focusing on vehicles, such as supporting e-mobility, can only succeed in making mobility more sustainable if also the electricity supply is based on renewable energy. Secondly, we emphasize that the stock flow service relations are a helpful angle for urban planning, as this broadens the view of resource efficiency of mobility. Thirdly, overall, also absolute reductions in distances traveled will be necessary to meet sustainability targets. This can also be achieved by redensification measures, for example. But also targeting trips to and from workplaces seems important, as they show a large share of motorized individual traffic use. Of course, and this is the fourth point, the future of mobility is not decided within Vienna alone, as the city is highly connected to its suburbs and hinterland. An integrated planning would help addressing this issue. And last but not least, relevant monitoring has to be improved, as data is still scarce, especially of mobility functions and services. To observe developments over time, a regular monitoring is necessary. Thank you very much for watching.